Okay, I have one more problem that I wanted to show you here in section 4.5. We're talking about curve sketching, and we're going through our list of 10 steps to sketch a graph. In the last video, we looked at an example of a function that had to deal with like an exponential, and so just the last one is an example of something with logarithms here. Let's sketch the graph of f of x equals ln x over x squared by going through the 10-step process here. Step 1, the domain of the function. Okay, I know I can't divide by 0. Also, I know I can't have a negative inside the logarithm there. So only positive numbers are going to be represented here in the domain. Okay, step 2, I need the intercepts. The x-intercepts, when I set the function equal to 0 and multiply both sides by x squared, ln x equals 0 means that x is 1, ln 1 is 0, right? And, okay, how about the y-intercepts? Well, I can't plug 0 in for x, right? We've already said that 0 is not in the domain, so there's going to be no point where the curve will cross or touch the y-axis there. 1, 0 would be my only intercept then. Okay, step 3, is there any symmetry? Well, if I replace x with a negative x squared is the same as x squared in the denominator, right? But the ln of negative x is not the same as the ln of x. Okay, so f of negative x and f of x would not be the same, therefore there's no symmetry to the y-axis. Okay. How about if I plug in negative x? Okay, negative x squared is the same as x squared, I mentioned. But is the ln of negative x the same as negative the ln of x? No. The ln of x to the negative first would be the same as negative the ln of x, but the ln of negative x is not the same as negative the ln of x. Okay, so this result here would not be true also. The function is not symmetric to the origin. Okay, there's no symmetry on this graph. How about step 4? We need the infinite limits and limits at infinity. Okay, well, we'd want to check for what's happening to the right of 0. Okay, and so I've set up a limit calculation. The limit as x approaches 0 further from the right of ln x over x squared. By the way, the direction is important here. We don't have a graph on the left side of 0, right? We've already stated that from the domain, so we'd want to indicate the direction. Now, be careful about this. We can't use L'Hopital's rule because we're not in indeterminate form. Okay, I have an issue with division by 0 here, right? We can see that easily. But the limit as x approaches 0 from the right of the ln of x, well, here's a graph of the y equal ln of x. If you're on the right side of 0, the y values are approaching negative infinity. So this is not indeterminate form, right? It's negative infinity over 0. That's not indeterminate form. But I think we already have our answer, right? Because we're approaching 0, the denominator is going to be a positive, a very small positive number, while the numerator is growing without a bound in the negative direction. Okay, well that's going to mean that negative infinity would be the result of that. Now let's take a look at what's happening as x is growing without a bound, okay, if x is approaching infinity. Limit as x approaches infinity of the ln of x over x squared. Now here we can use L'Hopital's rule, okay, since x is approaching without infinity means that the numerator and denominator would both be growing without a bound. You're in indeterminate form, infinity over infinity. And so I'm using L'Hopital's rule. L'Hopital's rule in this problem is my only option, by the way. You got the limit as x approaches infinity of the derivative of the top, that'd be 1 over x. The derivative of the bottom, that'd be 2x. Okay, if you flip the denominator, you can have limit as x approaches infinity of 1 over 2x squared. The denominator is going to be growing without a bound as the numerator just sits at 1. And so the y values are going to be getting very minuscule. The value of that limit is 0. All right, so we're going to have a vertical asymptote at x equals 0. This limit calculation tells us that. We're also going to have a horizontal asymptote at y equals 0. This limit calculation tells us that. An algebra student wouldn't be able to see that, right, because this is not a rational function. This isn't a function of the form polynomial over polynomial. So the only way to see these asymptotes here would be to know calculus, right, because we're working with limits. So now we're on to step 6. We need the first derivative. Okay, I'm going to use the quotient rule. So let's take the bottom, which is x squared, times the derivative of the top. That'd be 1 over x minus the top. That's ln of x times the derivative of the bottom is 2x. And this is all over the denominator squared. X squared squared would be x to the 4th. Okay, and now you can simplify that. X squared over x is x. Now I've got an x in common to these two groups, so let's go ahead and factor out x, and we can cancel it with one of the 4 x's in the denominator. That will leave me with an x cubed in the denominator. 1 minus 2 ln of x would be left in the numerator then. Okay, and if we set that equal to 0, multiply both sides by x cubed, and then add 2 ln x and divide by 2, you're looking at ln x equal 1/2. If you take e of both sides, e to the ln of x is x, and you're going to have e to the 1/2 then on the other side. E to the 1/2 is the same as the square root of e, and the square root of e in decimal form would be roughly 1.6. Okay, so I'll know where to position that, when I sketch my graph here. Step 7, we are using the first derivative test. So I've got my table set up here with the square root of e is the one and only critical number, and of course I'm starting at 0, right? Since we've already said that x can't be 0 or a negative, we'll start at 0, and I've got these 2 intervals. Square root of e is roughly 1.6. Okay, so a number between 0 and 1.6 is 1. If you plug 1 into the derivative, ln 1 is 0. So you'll have 1 over 1 is 1. And that means that you're going to be increasing on that part of the graph. If we were to let x be 2, okay, which is one number in this second interval here, then what do we get? Well, ln 2 is 0.69, roughly, times 2, that's going to be something bigger than 1. Okay, so 1 minus something bigger than 1 would mean that you'll have a negative in the numerator. 2 cubed is 8 in the denominator. A negative divided by 8 would be a negative. It'd be negative 0.05 if you were to, give the decimal form. But we know it's a negative. That means that we're going to be decreasing on that part of the graph. Okay, we're increasing and then decreasing. That means we'll produce a local max at x equal the square root of e. And to get the y value, when you plug in the square root of e into the function there, the ln of the square root of e, well, the ln of e to the 1/2, the power can come out of the logarithm there, and you'll have 1/2 ln of e, or that'd be 1/2, divided by the square root of e squared is e. Okay, so we have 1/2 divided by e, or that'd be 1 over 2e, which is roughly 0.18. Okay, and here's the exact coordinates there. Step 8, let's get the second derivative, and we'll need to use the quotient rule. So I'm starting that here. We got the bottom is x cubed times the derivative of the top, that'd be negative 2 times 1 over x, minus the top is 1 minus 2 ln x times the derivative of the bottom, that'd be 3x squared. All over the denominator squared, x cubed squared is x to the 6th. Simplify that. Okay. Now, x squared would be in common to these two groups. So I'm going to go ahead and factor out x squared and cancel that with part of the x to the 6th in the denominator. That'll leave me with x to the 4th in the denominator. Left over in the numerator, I'm going to have negative 2 minus 3 is negative 5, and then minus a negative means plus. 3 times 2 is 6 times ln x. Okay, set that equal to 0 and solve. If you multiply both sides by x to the 4th, that'll clear out the fraction there on the left. Add 5 and divide by 6, you got ln x equal 5/6. If you take e of both sides, then x would be equal to e to the power 5/6. Okay, and if you were to type that in the calculator, I was getting roughly 2.3 if you go nearest one digit. And so now I'm ready to set up the concavity test here. I've got my table, interval number chosen, value of f prime, and then the conclusion. E to the 5/6 is there on the number line. Of course, I don't want to include 0, right? Anything to the right of 0 is what we're representing. And that's going to split this into two intervals here. And now e to the 5/6, I mentioned that was roughly 2.3. Okay, so I can have an idea of what my test value should look like here. Number between 0 and 2.3 is 1, okay, and if I plug 1 into the second derivative, ln1 is 0, negative 5 over 1 is negative 5, okay, and we're concave down then on that part of the graph. A number bigger than 2.3, I used 3 here, so if I plug 3 into f double prime, the ln of 3 times 6 is going to be some number that is bigger than 5. Okay, so if you have some number bigger than 5 and you subtract 5, you'll have a positive left in the numerator there. Okay, 3 to the 4th is a positive in the denominator. So I've got a positive divided by a positive is a positive. The decimal that I was getting was 0.02 if you're to go nearest 2 digits on that. Okay, but that's a positive. That means we're concave up on that part of the graph. We're switching concavity once, and so therefore there's an inflection point at x equal e to the 5/6. And to get the y coordinate, I'm going to plug e to the 5/6 into the function. That's what I'm doing here. Okay, ln of e to the 5/6, the power can come out. Ln of e is 1, right? So that'll leave you with 5/6 there in the numerator. E to the 5/6 squared is e to the 5/3, and you can think of that as division by 1. So then when you flip the denominator, 5 divided by 6 times e to the 5/3 is what we get in the exact form. That's roughly 0.16 if you were to check that in decimal form. Okay, so here'd be the exact coordinates of the inflection point, and now I think I'm ready to sketch my graph here. So domain is all positive numbers. We do have an x-intercept at 1, 0, and there's no symmetry. The limit as x approaches 0 from the right of the function is negative infinity. Okay, so the curve is heading downward there if I'm on the right side of the vertical asymptote. We have a horizontal asymptote at y equals 0. Okay, and it looks like this curve will cross the asymptote once. Okay, this 0.10 is still on the graph. And, okay, we've got a local max at, so the square root of e is roughly 1.6. 1 over 2e is roughly 0.18. Okay, so at 1.6, come up to a height of 0.18. I've plotted that point there. That's a local max. We have an inflection point at what is roughly 2.3.16. Okay, so here's 2.3.16 is less than 0.18, right? So this point is going to be a little bit lower than the previous one here on the y-axis. And so that's where I'm switching concavity. We're concave down. If we are to the left of that, tangent lines all have to be above the curve. And we're concave up. If we are to the right of that point, tangent lines all have to be below the curve. Okay, and of course we got the asymptote there that the graph is approaching. Try to squeeze that in there. And so here'd be just a rough sketch of the graph of this curve. Okay. I feel that section 4.5 is a very good summary of everything that we've been doing here in calculus and good review for the algebra and trig stuff. Okay. Now these problems do take time. Okay, no doubt, because you're going through a list of 10 steps and you're doing a complete analysis on the graph of a function, but you're getting a pretty accurate graph though, right? You're getting a lot of key information here in these steps. Be sure to take a look at these problems here that are on page 321, the odd number problems listed.